Hi, my name is Lauren Baranowski. I'm a principal engineer at TDA Research. I'll be presenting today on my project to develop a novel hydrophobic and oleophobic coating that is designed to reduce heat exchanger fouling. This project is sponsored by NavAir. TDA Research is a small business in Colorado. We work on a wide variety of topics, and our expertise centers on the development and manufacture of advanced materials, the development of chemical processes, and aerospace and military hardware. TDA has a 30-year history of working within the SBIR program and commercializing the technologies we've developed. We hold 68 U.S. patents and 13 foreign patents, with a number of U.S. and foreign patents pending. I think our commitment to transitioning SBIR technology is really shown best by the numbers here. We've sold over $100 million in products based on our SBIR work, and we brought in over $261 million in Phase 3 investments. To do this, we leverage a number of key resources. Critical to this project is our deep expertise in coating development for aerospace and defense applications. We're located in the Denver, Colorado metro area, where we have 3 facilities, totaling around 80,000 square feet. These facilities contain extensive wet lab and benchtop space and analytical instrumentation, as well as our prototyping facilities and semi-pilot scale equipment. This allows us to cover the spectrum from early stage research to scale up and pilot level manufacturing. We have experience with several routes to commercialization, including both licensing and direct sales models, and we've taken a number of products through the mil-spec qualification process. The Navy Challenge. Heat exchangers are used in nearly every type of land and air vehicle to cool critical components such as the engine block. However, when the heat exchangers are fouled via the accumulation of dust and debris on the thermal transfer surfaces, or fins, the heat exchanger performance is reduced. The Navy seeks a cost-effective, durable technology to reduce this heat exchanger fouling. What's tricky here is that most heat exchangers have complicated internal fin geometries, as you can see in the bottom image. Thus, the desired coating must also come with a customized application method to evenly coat the heat exchanger fins. Our expected transition target is the V22 Osprey, which, as you can see, operates in very dusty environments. The coating needs to satisfy a number of requirements. The most critical is that the coating itself cannot decrease the heat exchanger efficiency. The coating must also be hydrophobic and oleophobic, so that it confers the desired self-cleaning functionality. The coating must also be abrasion resistant, so that it can operate in these dusty environments. The specific heat exchanger shown here, called the nacelle oil cooler assembly, is specified for an air intake velocity of 40 miles per hour, with a given concentration of sand and dust per cubic foot. Operational use and improvement. The naval aviation community strives for continuous improvement in the manufacturing arena. Current aluminum body heat exchangers are uncoated and accumulate large amounts of dirt and debris during typical use, as seen here. This type of fouling can significantly reduce the heat transfer efficiency and lead to overheating incidents of critical components. In this project, TDA Research has developed a self-cleaning coating that results in a 50% reduction of the heat exchanger fouling. You can think of this 50% reduction as a doubling of the service life of the heat exchanger before cleaning is required. Our coating also improves the cleanability of the heat exchanger, meaning that the maintenance of the heat exchanger will be easier as well. The solution. TDA Research has developed a self-cleaning coating that uses a custom blend of commercial resins and additives. Rather than developing and synthesizing our own resin, we chose to use commercial components and optimize the additive blends to confer the desired functionality. We decided to go this route because we really wanted to provide a solution that could easily be scaled up for commercial applications. Our coating system is water-based and does not include hazardous chemicals or solvents. We apply our coating via electrodeposition. This technique is a commonly used industrial process, particularly in the auto industry. The part to be coated is immersed into a coating bath and voltage is applied. This causes charged resin molecules in the bath to be driven towards the surface of the part, resulting in a thin, conformal coating. It is this technique that allows us to coat the complicated internal fin geometries of the heat exchangers. which is not something that could be achieved by a spray or dip application. We have found that our coating is abrasion resistant to sand and dust. We recently completed external validation testing of this, suggesting that our coating can last up to 1,000 hours in the specified environment. We've also taken our coating through a number of environmental exposures, including high and low temperatures, thermal shock, and water immersion, and demonstrated that the coating maintains both its physical properties and the self-cleaning functionality after these exposures. We've also tested the effects of the coating on heat transfer and seen that a coating thickness of up to 1 mil will not decrease heat exchanger efficiency. Most importantly, we've shown that our coating reduces heat exchanger fouling by 50% compared to an uncoated aluminum heat exchanger. Here we show a bare aluminum heat exchanger and a coated heat exchanger that have been fouled with an artificial soil, in this case a mixture of synthetic hydraulic fluid and AFRL test dust. We can see that the coated heat exchanger has lower fouling, meaning that less of the artificial soil adheres to the heat exchanger fins. After cleaning with a low-pressure water rinse, we also see that the coated heat exchanger is much easier to clean than the bare aluminum. Current status. This project is currently at a TRL of 4. We have applied the coating on small heat exchanger sections in a lab environment and thoroughly demonstrated the coating properties on flat coupons and on these small heat exchanger sections. This project is scheduled to end in June 2023, at which point we will be at a TRL of 6. This will involve the application of our coating on the nacelle oil cooler assembly from the V22 and a full demonstration of the coating properties at this scale. This project also includes a 1-year option period, running from July 2023 to June 2024. During this option period, we would demonstrate the thermal properties of a coated nacelle oil cooler assembly by actually putting that coated heat exchanger into a test aircraft at Pax River Naval Air Station. If the coated heat exchanger passes these tests, then it would move on to a field service evaluation for abrasion resistance and the self-cleaning properties. Key features, advantages, and benefits. The TDA coating results in a 50% reduction in heat exchanger fouling versus an uncoated heat exchanger. This can also be thought of as a doubling in the time required between cleaning intervals. Our coating also improves the cleanability of the heat exchanger. We use a cleaning efficiency metric, which is slightly under 50% for the uncoated aluminum heat exchanger, and this metric increases to 72% for the coated heat exchanger. A key feature of our coating is the low surface energy, which prevents buildup of fluids, dust, and dirt on the heat exchanger fins. This results in longer periods of trouble-free use, decreased maintenance costs, and could even allow for heat exchanger size reductions. The coating is water-based and non-toxic, which minimizes the chemical safety hazards, thus reducing costs for engineering controls, PPE, and training. The coating is applied via an electrodeposition method, which gives us a thin conformal coating even on non-line-of-sight surfaces. Electrodeposition is a commonly used industrial technique, meaning that it is cost-effective and easy to implement on a large scale. Transition to fleet. At the end of the Phase 2 project, in summer 2023, the TDA coating will be applied to a full-size V22 nacelle oil cooler assembly. We will also seek the Phase 2 option funding, which will cover thermal testing of the coated heat exchanger. This consists of installing the coated heat exchanger into a test aircraft at Pax River Naval Air Station. The test aircraft is then taken through ground maneuvers and limited flight testing, during which the heat exchanger temperature is monitored. This testing should demonstrate that our coating does not affect the heat transfer efficiency. Once this is complete, the coated heat exchangers will undergo a field service evaluation to determine the abrasion resistance and the expected reduction in heat exchanger fouling. This testing will give us a body of data that will drive the transition to the fleet. Market analysis. We are targeting commercialization of our coating via a licensing model. Although the coating is composed of commercial off-the-shelf products, TDA has developed unique expertise in the formulation and application of the coating. We see a number of potential commercial applications for our coating, in both the defense and civilian sectors. Our coating could benefit really any heat exchanger that encounters dirty, dusty, or abrasive conditions when the manufacturer operator wants to increase the maintenance intervals between heat exchanger cleanings. This could be things like off-highway vehicles, mining equipment, or other automotive applications. The application method we have developed is ideal for complicated parts and geometries that can't be coated using traditional methods like spraying or dipping. Transition and partnership pitch. TDA is looking for a prime contractor to partner with. The prime contractor would be interested in applying our coating to their heat exchangers during the manufacturing process. Since our initial target is the V22 Osprey nacelle oil cooler assembly, we are especially interested in prime contractors that produce this part. However, any prime that manufactures heat exchangers for NavAir use could also be a great partner. The role of the prime would be to provide heat exchangers for us to coat, and then they would assist with the necessary validation testing of the coated heat exchangers. In this partnership, TDA would be providing our unique coating formulation and the know-how for applying the coating. So, if this technology is of interest to you, please get in touch with us. TDA Research has developed a self-cleaning coating that reduces overall heat exchanger fouling by 75% without affecting the efficiency of the heat exchanger. We think this is a widely applicable technology that could provide benefit to the Navy and beyond. I'm the point of contact for this project, and you can find my contact information listed here. Hope to talk to you soon.